Okay, so here's what you really need to get out of these Taylor polynomials. So we talked about that definition. Now here's the deal. When you have a polynomial, then you have this remainder, right? And so the remainder is saying, okay, how close is this going to be to my actual function? So my polynomial here, this Taylor polynomial, is going to be f of x is equal to my polynomial centered here around a plus my remainder centered around this a. All right? So my function is going to be f of a plus f prime of a times x minus a. Looking familiar because this is what we just wrote down, but I want to get the other part in here. Plus the second derivative over 2 factorial x minus a squared plus this. The nth derivative of a times, over n factorial times x minus a to the n plus the next derivative, input c over n plus 1 factorial, and then x minus a to the n plus 1. Now here's the deal. Because I'm introducing this c, I have to define it. So this is where c is some number between a and x. All right, so you define c. So this first piece here is going to be the polynomial part. This second piece here is my remainder. So your remainder is what's left over, right? And so I'm saying what's left over here, some value c that's between my center and my actual function. So this x is my actual function. I'm saying between my center and my actual function. So here, oh, I put a's up here for the love of Pete. So here, my value in my polynomial, this is that extra, this is that leftover part. How close am I now from my polynomial to my actual function? And this is the formula that we're going to be using for those polynomials. So I want to note something. Note 0 factorial equals 1. So over here, whenever I have this f of a, this is because I'm technically dividing here by 0 factorial because I'm starting at 0. Remember, I'm going to scoot back a little. Remember, this is saying I'm going from 0, 1, 2, etc. So if that's the case, my 0 factorial, 1 factorial, and 1 factorial is just 1. That's why I don't have anything going until I start with my second derivative in 2 factorial. Because 0 factorial, 1 factorial, then 2 factorial, etc. Right? Depending on how many terms are in this polynomial, that's what's making the difference. Okay, now let's do some here so you can actually see what's playing out and what's going down right now. I'm going to move it to the next page just so that we have plenty of room. Oh, there's my graph that I'm going to show you here in just a minute of what this looks like. I'm going to stick it down here at the bottom so I want it to make sense to you. So let's do the math first, and then I'll show you like how this all plays out. All right, so here's example 2. I want to find the Taylor polynomial centered at x equals 0 for the function f of x is equal to sine of x. And I'm going to go with 4 terms. All right. This centered here part of it, I'm going to go black. This is the same thing as my a equals 0. That's the same concept that we're looking at. So centered at 0, that's going to be my a value. And then we go from there. Pardon me. Now, whenever I make this, I make a chart. Because 98% of success in mathematics is organization. I'm going to say, what is my term? What is the derivative? Then, what is that derivative evaluated at my center here? And in this instance, it's 0. So my center 0 is what's happening there. Because that way I can plug into those formulas. So let's come over here to the side and just refresh our formulas. My polynomial formula is the nth derivative centered at a divided by n factorial x minus a to the n. My remainder formula is the next one in line. Oops. See, I do that pretty much every time. C, and then you have to write this statement where a is less than c, which is less than x, but you're going to plug in your actual a here. So in this instance, it'll be 0, but this is just my generic formulas. Okay, so this piece is what's going to go in the numerator. So we're doing all of this work to get that numerator. Now I'm going for n equals 4 because that's what my problem is telling me we're doing. So this is a 4th degree, so the nth order, 4th order degree polynomial. So the first one is going to be 0 because it always, always, always starts at 0. Then I have the first derivative, second derivative, third derivative, fourth derivative, and then I put a double line there because the 5th derivative here is going to be my remainder. All right? Okay, so the 0 derivative here is just going to be my function, which is sine of x. So if I plug a 0 into sine of x, we get 0. All right? The derivative of sine is cosine. If I plug a 0 into the cosine of x, we get 1. The derivative of cosine is negative sine. Do you see what's happening? I'm just taking the next derivative. In order to take the next derivative, you have to take the derivative of the previous term. This is still 0. The derivative of negative sine is negative cosine. The derivative of negative cosine is positive sine. The derivative of positive sine is cosine. But remember, this is my remainder. So I have my input here is c because of that input. And I don't care about this last piece over here because I'm not plugging in a value. I'm saying the next term with c as my input. All right, let's write it up. I actually have the 4th degree polynomial is equal to 0, because this is my numerator, right? Let me pull it down just a little. My numerator over that factorial, x minus a to that. So I'm going to write this first one all out. Pardon me. I'm going to write this first one all out, and then we can see what happens here. So 0 over 0 factorial times x minus 0 to the 0. Beautiful. Plus. Now I have this next term. This is my next term here when n equals 0. Now I'm going to say when n is equal to 1. So I have my numerator here of 1 over 1 factorial x minus 0 to the 1. Because my a value here is still 0, and that's x minus a, right? This is n is equal to 1. Plus, then I take my numerator of 0 over 2 factorial x minus 0 squared when n is equal to 2. Plus, I have negative 1 over 3 factorial when x is equal to 0 cubed. Plus 0 over 4 factorial x minus 0 to the 4th plus my remainder here is that next term. So my numerator is this piece of it. So I actually have the cosine of c over 5 factorial x minus 0 to the 5th, and then we define that, where 0 is less than c, which is less than x. All right, now clean this up. Let me change my highlighter color. Let's go back to blue here. Ooh, we can make it a brighter blue. This is 0 times anything. What do you get? 0, right? Here, goodness sakes. Here I have 1 over 1, which is 1. X minus 0 is still x to the 1. So my first term here is actually, the 4th degree polynomial is 1x. Because I'm going to that 1. All right. Here, 0 times anything is 0. I know this also goes to 0. So my polynomial is a true polynomial, and I am making this up of minus. Now, this is 3 factorial. 3 factorial is 3 times 2 times 1, right? So put the actual answer in there. This is 1/6 x cubed. All right, don't write that 3 factorial. That's a super easy multiplication, so just do it. Same thing is happening right here. 5 times 4 times 3 times 2 times 1, 20 times 6, 120. Super easy math. So if you have super easy math, work with that. So this is the cosine of c over 120 x to the 5th, where 0 is less than c, which is less than x. And this is my answer. All right. If you have 0 terms, don't put a 0. Whoops. Don't put a 0 in there. Just you wouldn't write a plus 0 in a polynomial. Don't write one here, right? You just don't write one there. So this is what I want to show you. Oops. This is sine x. I'm going to make this big. Here is sine of x in black. That's my actual function. Well, I'm not messing with that. Here is if I were to look at a cubic. So if I'm seeing where red and black match up. Red and black match up all the way to here, which is fine if I only want to go from like pi over 4 to pi over 4, then that's all I want to do because it's a whole lot easier to work with a 3rd degree polynomial than a great big huge polynomial, right? So if I have that option, then that is what we're going to do. However, if I'm more concerned what's happening from negative pi to pi, that's not going to do it. And neither will blue, because blue matches up here and matches up to about here. Well, that's not taking me all the way to pi. If I'm concerned with pi, my 7th degree polynomial matches all the way up from negative pi to pi, and then I'm looking the difference. My remainder is this value c that hits what's going between my actual polynomial and my function. That is what we're talking about. So no, it's not a dead ringer for the entire function, but who cares? If I'm only concerned about centering around a, centering around this 0, if I just want to center around that 0, then how close do I need to be? Well, I don't know. What are you trying to look at, right? You trying to look at from negative pi over 4 to positive pi over 4? Then your cubic here, this degree of 3, totally fits the bill and does anything I need it to do. Frankly, even up super close here to pi over 2. Beyond that, that's not going to work. If I want to go all the way to pi, my 5th degree polynomial is not working either, but if I need like at 3 pi over 2, or what am I trying to say? Like 3/4, 3 pi over 4, like at the 3/4 mark, that would work. But not all the way out here. You see what's going on? So it really just matters how big of a segment am I looking for? How close does this polynomial need to be? And that's how you get this figured out. All right. That's the reality of the Taylor polynomials. Now we are sucking this in for our intents and purposes. If you actually had legit data that you're trying to work with, that is the whole purpose and reason behind a Taylor polynomial. In order to be able to apply this, you have to learn how to do it. And that's our job. In this class, our job is to learn the ins and outs of a Taylor polynomial. All right? That's our job. So we're not going to get crazy on this. We're not doing a whole bunch with this. Our job is to come up with different degrees of polynomial and make sure you can do that remainder. Practice this, get good at it, so that when you do come into a situation where you need to apply it, you'll be able to pull this tool right out of your toolbox and pull that off. All right? Okay.